Okay, section 5.5, the two-phase simplex. Well, this is actually a review of something we've already done in chapter 3, I think it was. So remember, the simplex algorithm, algorithm 5a requires that you have an initial basic feasible solution, an initial extreme point. For some problems, easy to do. For others, requires some more work. In section 3.6, we had two methods for doing that, the two-phase or the big M. And we're going to show you the two-phase here for the simplex, but you could also do a big M as well. So let's take a look at this example. Suppose we have this linear program, right? No problem. It's not in standard form though. This is good, all the variables non-negative, but we have some inequalities we need to transfer into equalities. Okay, so no problem. We add a slack here because we had something less than 9, so we added W5, or something bigger than 14, so we subtract a W6, and I forgot to write them, but all our WIs are there's now W1 through W6, they're all greater than or equal to 0. Okay, this is what we'd like to start with, but it's hard to see right off the bat what's going to satisfy these three constraints, and so we're going to form the phase 1 problem. Phase 1 problem says choose convenient values for your W1 through W6. And in this case, maybe we'll set everything to 0, except you don't have to do it this way, but except W5 equals 9, because it seems like that'll be a nice, easy way to satisfy the first equation. You could have set them all to 0, W1 through W6 to 0, and added a 7, 8, and 9. But I just decided to use the one that we had there. So we're going to choose this as our starting thing and see what's violated. So in the next constraint, if this is 0, this is 0, this is 0, we need to add an auxiliary variable. So we'll add a W7. We'll see if that gets satisfied. W7 and still equal to 14. Then the last one, 0, 0, 0, does not equal 1. So we need to add in the auxiliary variable W8. There are two auxiliaries that we've added. We want to then drive those things down to 0. If we can drive those to 0, that means what we're left with upon termination of this phase 1 problem, if we were able to, in the final solution, in the last two components, we have 0, 0. That means what is left over for the original variables, which in this case were 1, 2, 3, and 4, the first 4 components can be used as your initial basic feasible solution. So let's see what happens for that one. So again, here's our phase 1 problem. We could, an easy basis to choose right here, these will make an identity matrix. A basic feasible solution would then be setting x5 to 9, x7 to 14, x8 to 1. And the simplex on the phase 1 problem starts here. You can iterate by hand with the simplex and see what happens. But we're just going to jump in, assume that we had done this in MATLAB, throw the phase 1 into MATLAB to see are we feasible or infeasible. And so it's easy to pull off the entries that we would need for MATLAB. So maybe we'll make some space here. And just to review again how we're entering these, and this is a good way to check all your work because you have to do these by hand on paper with simplex, coded in MATLAB with simplex, and then you can always check your work with the simplex built-in routines. All right, so if we were trying to solve this in simplex, we need an objective function f. I'll write it as a row vector, but you could transpose it when you enter it into MATLAB. It'd be 1, 2, 3, 4, 5, 6, 7, 8. So there's W1, W2, all the way up to W7, W8, 8 variables. Your objective function vector is always n by 1, the number of variables n. A is there's 3 constraints, so this will be a 3 by 8 matrix. You pull off the coefficients, which this first column, second column minus 18, 0, 1, third column for W3 is 0, 1, minus 2. The fourth column is 0, 1, minus 3. Fifth column for W5 is 1, 0, 0. Sixth column with W6 we'll have a 0, -1, 0, 7th column for W7, 0, 1, 0, and 8th one, 0, 0, 1. And again, notice that we pulled off this to be basic, basic, basic. And see that hidden identity there, which again makes an easy initial starting feasible solution. The right-hand side is 9, 14, 1. What else do we need? Lower bounds. All of our lower bound LB will be a, again, you should write it as a column vector. You should prime that at the end. So this would be all zeros, or easier way to write it, just zeros. 8 by 1. Upper bound vector, infinity, or you can just make it empty. Infinity times ones, 8 by 1. Oh, this is AEQ, right? Because we're actually solving equalities BEQ. So A is empty, B is empty. Feed all that into MATLAB's linprog command. And let's see, I did that, and we get objective function value of 10 to the minus 11. So it gives, you ask it to spit out the objective value, and it gives a value of 10 to the minus 11. Okay, well, that's close enough to 0. That's saying W7 and W8 are actually 0. Therefore, the problem is feasible. You take in your X star vector, that is output. Let's make some space over here. MATLAB would input output, entering this to solve the phase 1. MATLAB will give a final solution, and it will have values. I think this is your, oh, sorry, X's is what we usually call them, but maybe we should call them W's for this example. W1 star, W2, W3, W4, 5, 6, 7, and 8. And we know that these two are both 0 because the objective function value is 0, sums to them. So there's values here, and you'll pull those off and start your phase 2. All right, so this is on algorithm 5B. Two-phase simplexes algorithm 5B, which is on page 247. So let's just take a look. But nothing new, really. It should be review for us, right? Okay, so the two-phase simplex. You start with your artificial model. We form the auxiliary problem with artificial variables. You're adding or subtracting those in for any violated constraints. You run the phase 1, which is the simplex that minimizes the sum of the artificial variables. That was our W7, W8. If phase 1 terminates with an objective function bigger than 0, stop. That means your original problem is infeasible. Again, for us and in practice, almost always that means there's something wrong with our modeling. If you're doing some theory, improving things, then possibly that might make sense. But what you're hoping is that it equals 0, and then you're going to take that, use the final phase 1 basis in the artificial model to identify a starting feasible basis for the original model. And then you go ahead and run phase 2. So now you've got that initial basic feasible solution, initial set of basic variables, and run away. And it should, there's only 2 choices at that point. You either get an optimal solution or you know the model's unbounded. So actually in practice, you can really think there's 3 things that could happen. Model could be infeasible, the original model. The model could have an optimal solution, one or many. We'll just get one with the simplex, and the model could be unbounded. Okay, let's take a look at one more example from this section. Let's look at this small one because it'll help us visualize. So we want to minimize this linear program. It's not in standard form. We need AX equal B. All the variables are non-negative. That's good. So we're going to add a slack and a surplus here. Standard form, and what you're hoping to do is there an initial basic feasible solution that satisfies these constraints that we can just quickly by inspection see? Sometimes you can fool around, trial and error, and get something, but here it's not going to happen. We need all our variables greater than 0. Well, we could set everybody to 0 except for y3 being 2. That satisfies the first equation, and it satisfies all the non-negativity. The problem is right here. This is a violated constraint. So we chose convenient values for our variables, and we still came up with a violated constraint. The trick to that then is to add your artificial variable y5 to this one, and therefore we can start with we can easily pull off for this one an initial basic feasible solution would be 0, 0, 2, 3, I'm sorry, 0, 3. Okay, so from this one right here, an initial easy initial basic feasible solution would be y 0, 0, 0, 2, 0, 3, right? Everybody's non-negative and it satisfies our two constraints. Then we're going to run the simplex on this. We can either run it by hand or we can run it with MATLAB on our phase 1 problem, starting with this initial basic feasible solution. You need that to do it by hand. MATLAB doesn't need initial BFS because it figures one out itself using techniques that we're doing, right? And if you do that, MATLAB terminates and it gives this as its optimal solution to the phase 1 problem, 20009. What can you conclude from this? You have enough information now. It shows you that y5 is 9. That's the best it could do. It could not drive it down to 0. It tried to minimize that auxiliary artificial variable. It couldn't. So that means your original problem was infeasible. Well, this one was small enough to go back and actually see, like we could do the graphical method. And again, for most of the time, that's infeasibility is going to say, hey, you've done something wrong here in your modeling. But this came from the textbook, so we know it's right. And it's just trying to verify something we could see visually. So let's take a look. y1, y2, we need y1 less than or equal to 3. Here, this side of that line. The first constraint satisfied an equality, that would be going through intercepts of 2 and 2. Oh, sorry, greater than equal on this one, this way. And 2 and 2 less than or equal. So here's the line y1 plus y2 equals 2. 0, 0 is on this side and satisfies it, so it means I'd shade this way. And then y1 and y2 greater than 0. So here is our feasible region on these edges, right? So in the non-negative octant, the part here and the part over here. This and this. What's the problem? Well, first of all, it's not a convex reason. It's impossible to satisfy this and this at the same time. And so this problem is infeasible. Which again, maybe for a bigger, easy for a small one, but for a bigger problem, you can't do that. That method isn't going to work, but this one will. The two-phase always does. Okay, a few problems from this section. Homework problems. Numbers 20A. 20A, 21A, and 22.